I'd like to just give you a general introduction to QED Naval and its technologies and the projects that we're working on within, Wales. So, without further ado, I'll give you some background with QED Naval. We're primarily a platform developer based on 20 years of naval research, knowledge and capability. I mean, our key strengths are within numerical modelling, using CFD and FEA techniques, but also combining that with the state-of-the-art experimental and scale testing capabilities. So we started this journey with the platform that I'll introduce in a few moments in 2012, and so it's been quite a long route to market. But in recent times, as Jay has already mentioned, we had the opportunity to acquire the Tocardo tidal turbines, which gave us a broader title as technology developers as opposed to platform developers. We encapsulated the knowledge and capabilities of Tocardo with over a decade's worth of tidal experience and data and knowledge that we picked up from that as well. As Jay mentioned, we did that as a JV with our partners, Hydrowing. That has been, a shining example of where collaboration within the industry has been most effective. And both companies required a turbine in order to demonstrate their platforms. And this was, a fantastic opportunity to use a tripartite relationship to exploit the values that are available within tidal. So shortly after the acquisition of Tocardo, we actually broadened ourselves even further, and we became project developers by acquiring Tocardo's flagship project, which is called the Shelter Tidal Project. Easy for me to say. We shortened that to OTP. This was acquired in late 2020. It was restarted. It was originally installed at the Shelter storm barrier in 2016. So it's been in near full-time operation for 6 years. It's had a single large maintenance intervention prior to us purchasing it. And we went through a whole technical due diligence review on that project before acquiring it as well. But it's notable to see that since acquisition, we have generated, and we're approaching up to a gigawatt hour of tidal energy. We use this platform really as a sales and R&D platform. But it does manage to pay its way because it has got a fully commercial PPA with Vattenfall. So it gives us amazing, and our engineers, and amazing training capabilities and intelligence of O&M strategies and stuff like that going forward. So it's a really solid and reliable turbine, and it's got the commercial acumen to go alongside it as well. So moving on to our Welsh projects, I'm delighted to say that we have submitted a berth allocation for Morlais, and today we managed to, I heard verbally that we've got a site that we applied for, so we got a berth to take forward to AR4 and AR5 and AR6. We've also formed a Welsh company, in order to develop that specific project. It's currently based down in Pembroke, where we have an operationals base, and I'll talk a little bit about that a bit later. So you can see there that the subzone of Morlais that we applied for is actually the GO3 berth. That has been strategically linked to the other berth, which is BL1, where there's very good site resource assessments. The reason why I mentioned that is because Hydroang have applied for AR4 round for the BL1 berth, and that opens up further collaboration possibilities about sharing marine ops and servicing, maintenance, even cable lay, all of these things. So it offers us great opportunity to offer value for money, to anyone who invests in these projects. So we'll be the turbines you saw in the OTP project are the T2 turbines, and we're currently developing the T2 SI, which is a sportsed up version, as the name would suggest. All of that's going really well, and we're looking for a UK supply chain for that specific turbine. So QED's main product is what we call the sub-hub. This is a picture of the technology demonstrator, which is a community scale device. It's capable of 240 kilowatts of energy. You see it there with a nominally shuttle-based turbine on it. So it's actually a generic platform. You can put any horizontal axis turbine, and it will be compatible. But its unique selling points are really this patented self-installing technology. So it's the submersible characteristics. So in the transit condition, we're primarily naval architects, so we've looked at the transit condition, the dive condition, and the on-bottom condition, through life. We've demonstrated that this is a low-cost installation and deployment platform, but also a low-cost to maintain. It takes, and it's been demonstrated to take 15 minutes to half an hour to go through the dive process. We've been testing that in Strandford Lough since 2018, so it's had 2 years in water, and we've got lots of O&M information from that. So that's great. The other key aspect of this is because it essentially is a foundation structure, but it's specifically hydrodynamically profiled to actually improve the site conditions. We can get as much as 20% increase in velocity, which, given the cubic law to power, is a significant increase in yield, and hence that has a big impact on the levelized cost of energy. We're really pleased with the way it's performing. This is just an example of in the dive condition. You see there ahead of the sub-hub that you've got a pretty modest installation vessel, which is essentially just a barge. The scenario is that a tug, just a standard harbour tug, with fairly reasonable day rates, can tow the whole assembly out in a single operation, and it can be installed over the course of a slack water or on the tide. It's important to point out that this has got wide weather, tidal and wave installation windows. Because it doesn't have a vertical connection, i.e. a lifting connection, it doesn't snatch at all. So waves doesn't impact the installation as much as it would do otherwise. One of the other benefits we feel of the sub-hub platform is that it's a subsea gravity base 95% of its time. And you can see it there within a very environmentally sensitive area within Strandford Lough, not least because you've got the local yacht club that can essentially sail over the top of it, with clear navigation channels. The other aspect of Strandford is an area of scientific interest and Natura 2000 site. So a lot of the environmental credentials we've worked with Queen's University Belfast and with the planners over in Northern Ireland there with DERA, we've got lots of evidence with regards to limited impact, and it's got a very benign impact on the seabed and the environment around it. So, in close of that particular project in Strandford Lough, we basically went through a whole decommissioning scenario where any moorings that we did leave were lifted, and you can see there that the sub-hub has the support structure stripped off it, along with the turbines. That was all done at sea in sheltered water, using a vessel similar to what you see there. Again, reasonably cheap vessel to charter for the day. It took us a day to remove all the turbines and the crossbeam. And then we picked up the mooring lines. All of this was consented, insured, fully bankable, project phase, whereby as part of the Tiger project, we have delivered the system from Strandford Lough to Pembroke, and now it is currently residing in Mainstay Marine Solutions Yard, where they've constructed a new crossbeam, which is what you see there. It's undergone a refit in Mainstay Yard. That is now complete, so I'm delighted to say that. And what we're doing there is basically bringing back up all the ballast systems, and we're doing all the commissioning and testing ashore before stripping it all down, launching it, and then towing it back as part of the Tiger project to the south coast of England. Our turbines, it's worth mentioning at this point, a very robust and reliable turbines with over a decade worth of in-water time as presented with the OTP, but this is the T1 turbine, which was formerly in the sluice gates in Dover. It's got this, the patented item on these turbines, and what makes it clever is what we call a bi-blade system, which gives its bidirectionality. So on the flood and the ebb tide, it's got a passive pitch changing mechanism, so it optimizes the performance of the turbines in each direction. Not only that, it's a direct drive, means no gearbox. You've got no gearbox losses, which can be both between 5 and 7%. It's also a permanent magnet generator, which makes it very efficient as well. You can get above 90% efficiency in the electrical transfer of these. So it's from our point of view, it's a cracking turbine. This is the barge is the minimum facilities that is required in order to install the sub-hub, as you saw in the previous pictures. Over the COVID crisis, it became quite difficult to acquire these barges, even to rent them, charter them, and it was a real project risk, and we had to move on. And delighted with the relationship that we had with Mainstay, and we've come up with a relationship in order to develop this barge for the installation of the sub-hub. But it enables QED to install and retrieve the sub-hub at will, and completely independently, and at low cost. Essentially, what we call the subsea manifold sits on the barge, and that allows us to plug into all the systems, be it the export cables, all the air, the hydraulics, everything from the safety of the vessel. And then we've got a small workboat which provides all the services like the generator and the air compressor in order to enact the installations and retrievals of the turbines. The final important bit of the test barge capabilities is that's where currently the power takeoff system is. So that's what we'll put, and it will be simulating the grid. So we'll have the site that we're going into in Yarmouth is not grid connected, so we have to be able to simulate the grid and load on that. So that's a quick example of the workboat. Again, a minimal facility that we operate, not only for crew transfer, but for providing the essential services, but we also are doing quite a lot of the site resource assessments. We've got the ADCP and ADV equipment in order to do those. And we do have drones and ROVs, and we would like to add some hydrophones in order to do full environmental monitoring of our projects. So as part of the Tiger project, again, we're looking at our next generation device. I mentioned earlier that the technical demonstrator you saw before was a community energy device. This next generation, we're looking at the magic megawatt and breaking the magic megawatt, and this will be a 1.2 megawatt device. This would be the device that we'll be installing at Morlice, along with the T2SI, which is a sportsed up version of what we've got over in Holland, operating on a daily basis. Yeah, I think that's enough to say about that. This is a slightly controversial slide, you know, in it's making some comparisons between tidal and offshore wind, if I dare, you know, is possibly asking the question, you know, why tidal, and where is the value in tidal, you know, above and beyond wind, and that's a really important, you know, question to ask. You know, in order to provide the government the capability to provide that incentive price, and to square that off with the fact that when the wind doesn't blow, where you're going to get your renewable energy. There's no other form of renewable energy that you can, you know, so when tidal is there is a danger that we can produce too much capacity for when the wind doesn't blow. We've got no other form of renewable energy to fill the gaps. So OREC have been doing quite a lot of research on this, along with UCL. And you know, the key stat there was they recently run a model of the national grid, and if we were to achieve the 11 gigawatts of tidal energy onto the grid, they have said that we would save over £2 billion of capacity charges. So that is, you know, a dramatic statement that you know, gives tidal a lot more value. Not only that, is that the UK supply chain really owns tidal, in my view, and I think there's great opportunities to take a much larger part of the value chain from tidal than there is in offshore wind. So that's where the value is. So that's me, and I'll hand back to Jay.
Thank you very much for that, Jeremy. Yeah, if you'd like to know more about Jeremy's technological solution, please by all means reach out to him. So last and by no means least for our technological showcase sessions, we have Tony Lewis from Ocean Energy. Now we have close sectoral links with other countries. It's not just projects that have been developed in Wales. We saw from some of our collaborators in Scotland earlier, and Tony is developing technology in Ireland and is being tested as far away as America, I believe. So I'll let you tell him a lot more. Let him tell you a lot more about that. Thank you.
Well, thanks, Jay, Pranam. It's really nice to have an invitation to come back to North Wales, and I'm very grateful to Marine Energy Wales for inviting me to this. I was thinking, this year it's 50 years since I graduated in the University of Bangor in physical oceanography, so a lot of things have happened in the meantime, and certainly a lot of the places that we were driving around 2 days ago were really quite unfamiliar to me because of the changes which have gone on. My name is Tony Lewis. I'm the Chief Technology Officer for a company called Ocean Energy, based in Ireland. And we're developing a floating oscillating water column wave energy technology. And we're moving forward the whole time, trying to build the projects, to de-risk the developments, and have a pathway towards commercialization. So Ocean Energy has been working through the TRLs with very small-scale testing back in around 2005. larger scale testing after that, and between 2009 and 2011, Ocean Energy was working on a deployment at the one-third scale benign site at Galway Bay in Ireland. And we built the device there, what we call the OE12. It was a 12-meter long device, rated at about 25-30 kilowatts. And that had 3 deployments, one without any turbine to generate electricity, just to measure the air power, the pneumatic power. We then tried experiments with a Wells turbine for the system, and we also then carried out a final set of work funded by the European Commission to look at a turbine developed by the Portuguese, which is an impulse turbine. So all of that went very, very well. The performance was good. The operations were very good. So that gave the company confidence to go to the next scale. Ireland doesn't have an opportunity for scaling up from the Galway Bay site. So we were fortunate that Ireland has a memorandum of understanding with the US Department of Energy. And so we managed to put together a co-funded project between the US Department of Energy and the Irish government. And that has enabled us to build what we call the OE35, which is a 35-meter long device, and that has an installed capacity at the present time of 500 kilowatts, but has the option to scale up to 1 megawatt. We've partnered with Dresser-Rand, who have then been taken over by Siemens, for the turbine which they have, which is a very high-efficiency turbine and has very good reliability with only one moving part. So the basis of our device then is a large box, if you like, or a barge type system with an air chamber connected to the open sea underneath. The air chamber then receives pressurization by the waves and pumps air through an air turbine. It's a very simple concept. The device there is with the pneumatic turbine from Siemens in the schematic. The device, as I say, in this case is 35 meters long and there produces the electricity by pumping air through this air turbine. The air turbine obviously has to be of a special kind because the air is being exhaled and drawn back in again, so the turbine turns in the same direction independently of the direction of the airflow. So this Siemens turbine is highly efficient at doing that. In terms of the testing in Galway Bay, as always, we deployed that in the New Year time of 2007 and 2006-2007. And 3 days after the deployment, we had the 40-year design storm in Galway Bay. So that was a bit of a challenge, but fortunately there were no problems there at all. The mooring designers suggested that we should have had 35 tons of force on the moorings. We actually measured 4 tons, so that shows the device works in a very strange way in that because the submerged oscillating water column faces backwards, then the device acts a bit like a jet boat and pushes itself into the big waves, reducing the mooring forces. So the survivability capability of the device is extremely high, and that was proven in the Galway Bay trials. So we had very good power performance, power absorption with the Galway Bay site, which then gave the company, as I say, a lot of confidence in moving forward to scale up to the next size, which is the OE35, the 35-meter device, which in the deployment we have in Hawaii, which I'll describe in a minute, will produce about 500 kilowatts of power. But in a more exposed site like South Wales or EMEC, it will produce over 1 megawatt. So the device is 35 meters long, 18 meters wide, has a draft of around 10 meters. And in this artist's impression, all the orange part is under the water. So the visual impact is quite low because the amount of the structure that is above the water is relatively small. So just a short video to show you the construction. We constructed the device in Oregon, again funded by the DOE in the US and by the Irish government. It didn't actually get built as fast as this. I wish it had, but this shows the operation in the shipyard in Oregon. It was a location where the Liberty ships were built in the last war. They were building a ship a week at that time. These guys are moving bits of steel around the biggest piece there, which they're just lifting up now to put together at the front. That weighed 350 tons. And you can see the guys are moving it around as if it's a small toy. So the whole thing was assembled in 3 parts. This is the Siemens turbine then, with the generator being fitted, permanent magnet generator, so highly reliable system. The only disadvantage of the Siemens turbine is that the air ducting is very large diameter, so we had to accommodate that into the design. So I just put this in just in case the video didn't work, but fortunately the video worked. So that left us then with a device sitting on the harbour in Portland. All of the equipment on the device is industry standard. There's no experimental equipment at all. It's all standard electrical equipment used in power systems all over the world. We have a big VFD system to control the voltage and the frequency. And then we have an 11 kV transformer, which gives us then the power export at grid scale of 11 kV, and you can see that in the picture of the transformer system. All of this is inside in the buoyancy chamber. There's a big buoyancy tank, so all of this is contained there, away from the water, away from the exposure to the sea, and in a nice, reasonable dry environment. So that's the equipment. The launching then in this next video shows the launch out from the shipyard. Total weight of the steel there about 750 tons, and the turbine then fitted on the top. Again, you can see these guys wheeling this thing around as if it was a small toy. They're certainly very adept at moving things. We had a problem with global warming because the river levels in the Colorado River at that time have been very, very low compared to the normals, and so they're having big problems there. So we actually had to double handle this device. We had to handle it onto a barge because the level of the water wasn't high enough to put it straight onto the dry dock. So we had to put it onto a barge, move away, bring the dry dock back, and slide it off the barge onto the dry dock for the final launching. So the 2-phase launching, which wouldn't be required in the normal run of things. And here you see the device then being taken out of the dry dock. So the test site is in Oahu in Hawaii. The test site is operated by the US Navy and is provided free of charge to projects which are funded by the US Department of Energy. It's a 1 megawatt grid-connected test site with 2 berths, having cables laid to the berth themselves. They also provide the moorings free of charge, and they designed the moorings to be suitable for our device. So we've really benefited, I think, from that collaboration with the Navy on that site. That's the location of the site there on the northeast coast of Oahu in Kaneohe Bay. So this is the device then ready to go from Portland. We decided to do a wet tow from Portland to Hawaii. I'm glad I wasn't on the trip. It took a very long time, 43 days, with a trip of about 2,500 nautical miles. Some of the times they were only going at 1 or 2 knots because the waves were quite big during the tow. But fortunately, the device arrived in Hawaii, and we had the berth with the help of the Navy at Pearl Harbor, where the device was arrived around the 10th or 15th of December 2019. So we went through all of the the procedure of having a traditional Hawaiian blessing, which was essential apparently because of the nations thing. The Americans are very big on these Third Nations type things, so we had to go through that, and so that was very positive. So this just summarizes some of the partners that we have, mainly Siemens and ourselves, funded by the Department of Energy and SEAI in Ireland and the US Navy. So the device constructed in Portland, leaves Portland, arrives Hawaii December 2019, and the plan is to do the commissioning and installation January, February 2020. We made the mistake of coming home for Christmas, and we haven't been back. So COVID caught us at that stage, so our machine is now sitting still in Hawaii. As I say, we unfortunately were not able to go. The Hawaiian authorities have been very, very close about access with the COVID problem. So we now believe that we're going to rekindle the project. The Department of Energy and SAAI have maintained the balance of funding for us, which is positive. And we expect now to go back at the beginning of April and start the whole process again, if you like. Probably have to do some dry docking, some checking and so on. So we expect around Q4 of 2022, that's this year, thank God, when we will do the deployment. So we're delayed about 2.5 years, which is extremely frustrating. So the device now is sitting in Honolulu because we had to move out of Pearl Harbor because the US Navy needed the berths. So it's sitting alongside there in Honolulu, just awaiting our restart, if you like, of the project. And we expect to do that, as I said, to deploy now by at least sort of October of this year. We've just got a very basic maintenance ongoing. We've been turning the turbine by hand to make sure the bearings aren't seized up in any way. And we've certainly been inspecting the moorings and so on. But it's virtually just been sitting there for 2.5 years, which, as I said before, extremely frustrating. So the next steps then, we expect to be on site for a year at the Navy test site. And then after that, we want to really transfer the device to a more energetic site. As I said, in the Hawaii site, we'll produce about 500 kilowatts. The same size machine, the OE35, will produce a megawatt or maybe even 1.2 megawatts in a site like EMEC or maybe Southwest Wales. So we're certainly actively looking for a follow-on project in 2024 for the deployment at a more energetic site. So hopefully in the future we might be able to come to Wales and see a fruition of the project being carried forward. So thanks for your attention, and I hope you enjoyed the story, and I hope you commiserate with us over the problems associated with COVID. Thanks very much.